Uh, we're about to start. So welcome everybody to the September edition of Ithaca Fest. The first speaker was supposed to be Alan Cigoli, but he was not able to come today. And so we have his co-author, Giuseppe Metere from the University of Palermo. It's joint work, so he's going to talk about exactly the same project, which is Groupal Pseudofunctors. Please, Beppe, go ahead.
Hello, everybody. So I'm really sorry you want to enjoy Alan's talk, which will have been much better than mine, of course. And so I will try to do something, but we were lucky because it's a joint work, and more luckily, since I gave a talk about this stuff a couple of weeks ago, and I'm sorry for people like Paolo, Saracco, that were listening to, that were attending that conference, so we'll have a photocopy talk, because indeed I had this piece of news of Alan was not feeling very well just a couple of hours ago. So the talk will be exactly the same. Usually I try to make some differences when I replay a talk, but in this way, this time I'm really sorry for that. But anyway, I hope that and also this September 20, yes. And I just could just change the first slide to put Ithaca Fest. But nevertheless, I hope the talk will be enjoyable for you, because not because of me, because the project is very interesting, in my opinion, with Alan, already said, and with Sandra Mantovani. This is a joint work. So I try to make this windows disappear. Yes, I cannot, so I will make this disappear this way. Yes.
We are not seeing what.
Yes, I know, but I did. I mean, I was seeing just in front of my slide, so I couldn't start. Okay, so I'm starting. Stop joking. Groupal Pseudofunctors. This is the talk I'm talking about today. So let's start. I'm starting with a very short introduction to internal algebraic structures in a category. So one thing I think I've been thinking since I was studying this stuff when I was a student is that one good reason to study monoidal categories is that you can define internal monoids in the category, and more generally you can define some kind of algebraic structures. So everybody knows how it goes, but I'm just recalling that whenever, by the way, can you see my little, my little hand?
Yes,
on the
we
screen?
can.
Oh, excellent. So as I was saying, everybody, we know, we can describe a monoid with diagrams. In the case of a monoidal category, where the monoidal product is this O times, and the identity is the I, the I letter, capital I. So we can describe a monoid object with a bunch of diagrams that express the associativity and the neutrality of identity of the monoid object. Moreover, if well, here I am cheating a bit, because if the monoid category has some more structure, you can define a symmetry, internal symmetry for the monoid, and this is the case, for instance, when we take the Cartesian monoidal structure, so the monoidal structure given by the Cartesian, the categorical product, the limit. And in this case, you can define also a notion of commutative monoid. And well-known examples are usual monoids, but you can also take internal structure, for instance, in groups. You get abelian groups, and you can take monoid in abelian groups with respect to the tensor product. Then you get unitary ring, for instance. So it's quite a powerful notion, and well, as I was saying, some more features can be obtained where the category is a special monoidal category, so it's a Cartesian monoidal. In that case, you can, for instance, define internal groups. And in order to have internal group, you must have this more structure, that is the inverse map, this M to M. And since we want it to behave like an inverse, you duplicate, and you put the inverse on the side, and then you multiply on the left side and on the right side. You must obtain identity. So these two diagrams express precisely this fact. All right. So far, so good. A good thing, I could have written here, a good reason to study monoidal functors is that they send monoids to monoids. And by the way, this is also a good reason why when you study lax monoidal, you have the lax, so the good one in that direction, and the oplax or colax in the other direction. So because with this direction, with the lax direction, you can actually send monoids to monoids. A very special case is when you get a category with final product and a functor that preserves product from B to set. Well, in this case, you can easily well, here I'm assuming that the preservation is strict, and then you can actually define a monoid structure on the image f of m, just taking the f of the composition of the operation, I would say. Okay, and what does it mean? This means that this functor, the product preserving functor f, lifts to the category of internal monoids. Well, one magic that happens in this case is that with the same assumption, only the preservation of final products, the same functor f lifts to internal groups and to abelian groups. So this, on the vertical sides here and here, we have the usual forgetful functors from these internal categorical functors and so on. So if it's more special case, and whenever, for instance, the forgetful functor from abelian groups, internal abelian groups, to B is the identity, and this happens, for instance, when the category B is abelian, and so every object is endowed with a unique abelian group structure. I would say, well, in this case, the diagram means that the functor f lifts to, factors through the forgetful functor from the abelian groups to sets. Okay, this is a very special situation, and we want to study what happens if we try to reproduce these facts in dimension 2. In a higher dimension. Okay, so why? Because when we try to generalize some result, we must have very good motivation. I mean, I think this is my point of view, not just generalization for without purposes. That doesn't give you the direction to follow. So there is a very good reason, at least in my opinion, a very good motivating example for doing this job, which is in this old work by Nobuo Yoneda in 1960, very influential in homological algebra, when he proposed a categorical setting to study cohomology even in categories without projectives. So traditionally, cohomology was studied by taking projective or injective resolutions. And but you have a situation where you don't have these projectives, enough projectives, and so how can you do? You can actually study cohomology, and you can do it by using so-called n extensions, extensions of length n. So if B is an abelian category, and we can take an object A in B and define this functor x to the n A blank, and this takes any object B to the connected components of n extensions. Extension means exact sequence, right? in the abelian category. In this case, we take the abelian category, but Yoneda was generalized a bit more with additive situations. But we take things easy for just for saying these motivating examples. And I was saying we have this notion of n sequences, so you can put a B and you can compute all the sequences from B to A, exact sequences, and then you can define in obvious way what is a morphism of sequences that fixes B and A, right? And you can take the equivalence relation generated by connectedness. Okay, and we have this connected the sets of you have this equivalence classes, right? And you send B to this equivalence class. Okay, to the set of equivalent classes. Sorry, and what happens is that since this functor in set preserves final product. And since in the abelian category, the abelian objects in B coincides with the category B itself, we apply the result and we get the factorization through the category of abelian groups. And surprise, the abelian group structure that you obtain on the set X10 AB, this one, is that is usually known with Baer products or Baer products, I don't know. Okay, so why going one dimension up? Because here we have taken a quotient, and so it's natural to ask what happens if we don't take that quotient. What kind? So in that case we have this pseudofunctor, because capital X10 AB is no longer just a set, but it's a category whose this other thing is the Poincaré category of that by category you get with this notion, and in this pseudofunctor you get categories, okay, and so you ask if those categories are endowed with some structure that when you quotient you get monoidal or group monoids of groups. So what kind of structure have this functor? Okay, so we can go to the higher dimension and see what happens with internal pseudomonoid objects. So similarly to the one-dimensional case, I would say that one good reason to study monoidal two categories is that you can define internal pseudomonoid objects. So what is a pseudomonoid in a two category? We find a product. It is an object M endowed with some structure, so a multiplication and identity, that satisfy some diagrams up to ISO 2 cells. These two isomorphisms alpha, lambda, and rho that fill the diagrams, and of course these have to obey to some coherence that I am omitting from here. For instance, a very good example, a motivating example of this construction is that a pseudomonoid in cat is nothing but a monoidal category. Another example we need in this talk is a trivial one, but important. If you take a category B, we find a product, then you can consider the category as a two category with trivial two cells, and it is a symmetric monoidal, two monoidal two category with the product, and then a pseudomonoid in B is just an ordinary monoid. Okay, so a good thing about monoidal pseudofunctor what are these pseudofunctors? So a pseudofunctor is a weak to functor, we know. That means that preserve the two categorical structures up to isomorphism. So we have this the composition and the identity of the category. And this is a special case because the category B is really a category, not a two category. So it's considered as a two category, but it's a category. The two functor is a lax monoidal with respect to the Cartesian structures. So I'm taking this very special case of the general definition. When you have these two pseudo-natural transformation R and R1, okay, these are really from this side, which is the product of f of A and f of B for two objects A and B, and f of the product, and similarly for the identity. So we have these components and suitable modification, which are quite involved, so didn't fit in this page, but indeed fit this other page. So okay, we don't have to read all the details, but we have these constraints, and also those have to obey to some coherence conditions that won't fit another couple of pages, and so I gave up, but you can find them. Okay, but in any case, the important thing that the monoid, two-monoidal pseudofunctor is something that preserves the two-monoidal structure of the two categories. And the good news is that monoidal pseudofunctor take pseudomonoids to pseudomonoids, and in particular for a Cartesian monoidal structure, they can take commutative monoids in B, which are pseudomonoid in the two category B, the category B seen as a two category, two symmetric monoidal categories, and that's why I was saying the direction of the R is important. All right. Okay, so we have something similar to what happened in the case of functors to sets, and the good news is this, so that F, we can write this saying that F lift to internal monoid and monoidal categories. So this means that the image of the multiplication of the monoid gives a monoidal category structure on the image of any object of B. So this lifts at this level. So the question is if we can lift it higher, and in particular, we have to feel what to put in these two rectangles instead of the question marks, and eventually see that it lifts to what we have decided to put in the triangle. So this is a question we try to answer in this talk. Before doing that, in order to do that, we have to define internal pseudogroups. Why? Because the idea is that as far as we put here the internal pseudomonoids in cat, instead of groups, here we expect to find the categorical version of groups. So internal pseudogroups. So they have been introduced by Bayes and Lauda in 2004, and they were called weak two groups, or simply two groups. And if you see the definition, indeed you have this diagram, which is similar to the one that defines internal groups, but instead of having commutativity, we have these two cells, and that are isomorphism, and they satisfy some coherence. And as I was saying, this was defined by John Bayes and Aaron Lauda, but the notion of pseudogroup already existed before, and it's due to this mathematician, which was at the time a student of Alexander Grothendieck. She's Huang Xuanxing, and in 1975, she wrote, she presented her PhD thesis. She was writing that before, possibly, and introduced this group category en français, category with a group structure that are monoidal groupoids, where every object has a pseudo inverse with respect to the tensor product. Now, a natural question that arises is why monodal groupoids and not just monodal categories? I would expect you define monodal categories and impose that every object has an inverse, you get what is deserved to be called a pseudogroup. Well, the fact is that if G is a pseudogroup in cat, then all its one cells are invertible with respect to composition. This is a surprise, actually, yes. So that it is indeed a groupoid. And this was observed in the paper by John Bites and Aaron Lauda. I asked John Bites about whether this was an original result or was already known. I think it was already known. John told me that he was told this by James Dolan, but he doesn't know where he took this information. But I don't know if, for instance, Hong Wang-Xin was aware of it, because she was not interested in this point of view, for instance. And this is a very interesting thing to investigate, I think, historically, I mean. By the way, so why do this happen? Why, if you take a pseudogroup, I mean, I take a monodal pseudomonoid and I impose all objects to be invertible, then I get also something that has arrows that are invertible with respect to composition. The idea is that when you want, I call this the inverse map. So the map that assigns to every, it's very sensible, this tablet, this mouse. I was saying that assigns to every object of G its pseudo-inverse. Okay, if I want this assignment to be a covariant functor, internal in categories, so in the two category of categories, so a functor, covariant of course, then I get, for magic, for a proof, that the arrows are invertible. Requiring just that objects are pseudo-invertible in a monodal category produces indeed a contravariant functor. A baby example to understand this point, even if it's a bit, is the preorders seen as a two category. So what are preorders? Are a preordered group, the category of preordered groups. What is a preordered group is an internal pseudomonoid in the category of preorders, which happens to be a group. In fact, the inversion map, the one that assigns to every element of the group its inverse, is antitone, so it's contravariant categorically. And if we impose the inversion map to be monotone, what happens is that a preorder is actually an equivalence relation. So it's a groupoid. Okay? A preorder which is a groupoid is an equivalence relation. So this is the phenomenon happens and is like a motivation. So we found some good candidates. I didn't explain everything about symmetric two groups, but it's something that you can imagine, like a billion groups. And so we could fill the column on the right-hand side with these forgetful two functors from symmetric categorical two groups, categorical groups also are called, two groups, two monodal categories. They forget part of the structure. Okay, and we have this lift with the only some assumption of F, with a few assumptions of F. So now we have to see if this actually lift to two groups and to abelian group and symmetric two groups. Okay, so do all Cartesian monodal pseudofunctors take abelian groups to symmetric two groups? The answer is no. So it does not lift the result from dimension 1 to dimension 2 without additional assumption in general. As an instance, you can consider as an example the pseudofunctor which assigns to every abelian group the poset, the lattice of its subobject. And well, in this case, you obtain actually symmetric monoidal structure on these categories of subobjects of this, but which is given by the join of subobject. But of course, this is not a groupoid. So for what we said in the last slides, it cannot be a two group. So, and this is a functor which preserves, which is a Cartesian monoidal. So preserves the product up to. So, so what to do? We study the preservation of group-like structure. This is the last part of my talk. So we'll see how this preservation of group-like structure lived. So this is a good point to ask a possibly question, if there are any. Or if not, you know, you are keeping the question for the end of the talk. We can go on. So this example I just explained of the subobjects makes the following definition sensible. The following definition is that what is a Groupal pseudofunctor? So a lax monoidal pseudofunctor between Cartesian two categories, in this case from a category which a Cartesian structure and a two category cut in this case, is called Groupal precisely if it lifts to a pseudofunctor that makes the diagram commute, and I forgot to put the f hat in the diagram, but of course you know that is this one. Okay, when this is the case, it restricts to abelian group and symmetric to groups for free. This is very easy to see. So now I want to characterize and maybe try to explain these Groupal pseudofunctors. Okay. So before I go on, there is a sort of disclaimer I have to take. Because we know that there is a canonical way to translate a pseudofunctor into Grothendieck fibrations, the so-called Grothendieck-Benabou construction. And Benabou point of view on it is very, very well known. For instance, we can read on Strike account on Benabou fibration. This was written when Benabou was still alive, and he was approving this. And he says that one may feel forced to accept pseudofunctors as the ensuring bureaucracy handling of canonical isomorphisms. However, as we show immediately, one may replace pseudofunctors H by fibration, where this bureaucracy will turn out as likely hidden from us. So the idea is that you shouldn't deal with pseudofunctor unless it is strictly necessary. And indeed, I approve this. And why? Because for many reasons. Okay, I won't enter in the debate, but I would say that in our paper, this is why I write this. That is our take, with me and with Alan and Sandra. Our papers are full of vibrational techniques. It's much better to see things under the vibrational point of view when you want to understand what's going on and to prove the results. On the other hand, since I want to focus now on the dimension leap, so the rising the dimension, in that case, the conceptual point of view is more evident when you see the pseudofunctorial point of view. Well, at least this is my point of view, but there are vibrations everywhere, and it can be easy to prepare this talk hiding all the vibration point of view, and these vibrations are under the carpet. In any case, the paper is online on the archive, and you can see all the vibrations that I have hidden in this talk are written down in the paper. Okay, so let's take I will recall the results we have achieved in this paper. The first fact, which was not obvious to me at was at all, is that if you consider any pseudofunctor from B to cat, being which I find a product and cat, then any pseudofunctor is endowed with a Hoplack symmetry monoidal structure, which is given by the universal property of the products. So that's why it's there everywhere. So any pseudofunctor is Hoplack. This is the first surprise, at least for me, for us. This is the first fact. So we have the following result. If we take a category, we find a product and a pseudofunctor from B to cat, then having for these L1 and L right adjoints in the home to cats of pseudofunctor for I to cat and pseudofunctor from B times B to cat, let's okay, it's possible to see this here. You can see that L is an R is an arrow in the two category of pseudofunctor from B to B to cat. All right, so this one cell can have an adjoint, internal adjoints in the two category. Well, in this case, that when you have adjoints, this is the same as saying that F is Cartesian, so that it has is endowed with a Lax symmetric monoidal structure, R1 and so on, from Bx to B cross to cat cross, in a way such that computing RAB on pair x, y, so x and y live in f of a and y live in f of b, gives a product. And someone could ask, this is strange, isn't it? I mean, these x and y live in two different categories. We have a function in cat. So I take x and y in f of a and f of b, which are two different unrelated categories in principle in cat. So how can you make the product? So the categories really are not unrelated, because there is something under the carpet. You see the carpet. And I said that I was hiding something under the carpet. And indeed, I was hiding the Grothendieck construction. So indeed, the x and y are objects in a category, in the total category of the fibration over B. So this is the condition I have to write down. In this case, so we have characterization of this kind of pseudofunctors. I go on, I'm a bit late. And then, when we have a Cartesian Lax symmetric monoidal pseudofunctor as before, then we have a characterization of when F is Groupal. And F is Groupal if and only if the units of the adjunction I was talking about, so eta 1 for the adjunction of R1 and L1, and the units of this RAA and RAA, in this case, I mean, not for all A but for all A in B supporting an integral group structure, are isomorphisms. So, to be short, the functor is Groupal if and only if the units of the adjunction are isomorphism. And the proof is, just as an idea, the idea is I send the inverse, see this inv I and V is the inverse map of the group, the internal group A. I send this inverse in order to construct an inverse of the monoidal category. And when I do this, in this very big diagram, I want to be filled with a natural isomorphism. I have this eta and eta AA. and they are not in general isomorphism. So when they are isomorphism, all the thing gets an isomorphism, and you can prove also the other way around. So this is the idea. So indeed, is what we expect. The inverse map gives the inverse map for the case of pseudo group. Okay, so we have a corollary. The case we were studying was where the category B was abelian. And in this case, when the category, for instance, when the category is abelian, more generally when the forgetful functor from the abelian objects is an identity, to be is an identity, and f is a Cartesian pseudofunctor, then we have that the functor f lifts to groupoids if and only if it lifts to symmetric to groups, which is quite, if you see this way, I mean, lift to groupoids means simply that f of every object is a groupoid. It's a category which is a groupoid. And in this case, it's automatic that gets a symmetric two-group structure, monoidal and everything. Okay, at this level, it is not even monoidal, the object. Okay, back to Yoneda, yes. Coming back to the example I started with, remember we had this functor which assigns to every object B the set the category of n sequences, n exact sequences from B to A, all right, which are called n-fold extensions. Okay, so we have to divide to study separately the cases. When n is equal to 1, then for every B in B, each X1AB is a groupoid. Why? Because of the five lemma, the short five lemma. So we have extensions, the usual extensions of A and B, and then where we have an arrow in the middle, it's automatically an isomorphism. And then, since it is a groupoid, the pseudofunctor is Groupal. And B induces symmetric two-group structure on each X1AB. And in this case, the pi zero of this X is the cohomology group H2AB, the usual cohomology. And when n is greater than 1, so for 2 extension, 3 extension, n extension, and so on, then these categories are not groupoid in general. And so the pseudofunctor is not Groupal, so that B only induces a symmetric monoidal structure on this X10. In any case, I won't enter into details of this, but in any case, even if these X10 are not groupoid, you can make them groupoids in a standard way by taking the category of fractions, and the category of fractions with respect to these weak equivalences, because you have identity on the top and on the bottom of the sequences, and in this case you recover, you get weak two groups. So the category of fractions that you obtain are weak two groups, monoidal structure, and again by taking the pi zero you recover the cohomology group H to the n of AB in this case. For n greater than 2, greater the 1, which is a mistake here. Yes. Okay, and in a similar way, you can deal with non-abelian cohomology. This example was taken by from Yoneda because it's easy to tell, but there is all another story of non-abelian cohomology, which is, and there are interpretations of non-abelian cohomology that can be made with the help of so-called crossed n-fold extensions, which have been defined in the case of group, of the algebras, and other algebraic situations. And we also have, in the bibliography, the references, there are some reference of ours when we extend all this stuff to strongly semi-abelian category in general, so to other algebraic situations. And you can use this for interpreting cohomology in that cases, and it works also for those. So you get non-abelian cohomology recovered in the similar way, but then it's impossible not to speak of regression. So I'm stopping here. I have some reference I like to point out, not only the cited references in the talk, but also called these fibered references, which are the papers that we have, where we have developed this theory since a couple of years. Okay, that's all. Thank you.
Okay, thank you very much for the great talk. I see there's a lot of virtual clapping hands. All right, so are there any questions? Feel free to raise your hand, unmute yourself, or write in the chat. While you people think about it, I have one question. So usually if you want a functor to map, say monoids into monoids, a slightly different approach, but related, is instead of using monoidal categories, is using multi-categories. And to have group objects, one needs something like hope functors or things like that. Do you think one can give a higher dimensional picture in that context similar to the one you have given for the monoidal category case?
So if you ask me for an opinion about this, I have to admit that I don't have enough knowledge of this for having a strong opinion about that. I thought about that a little bit because, well, this talk was presented in a conference about off algebras and monoidal categories. And indeed, one question I wouldn't dare to answer, but luckily nobody asked me this at the conference, was can you do this for internal Hopf algebras? And so my opinion is not strong, but it's positive. I think so. And I don't know which is the correct approach. Maybe that in the case of to generalize to Hopf algebras to a situation where you don't have just the Cartesian structure, Cartesian monoidal, but in general, it's maybe it's easier to deal with multi-category instead of monoidal categories with antipode and so on.
Right. Okay. Yeah, makes sense. Yeah. Thank you very much. All right. Are there any questions from the actual audience?
I have maybe it's more of a comment.
Please go ahead.
So it's I'm not even sure how relevant that is, but regarding what you said in the first part, that about the invertibility of one cells in a pseudomonoid. So again, I'm not sure how related that is, but maybe maybe you can tell me. In the case of enriched categories, when we consider groupoids and we enrich them in categories, then we automatically get actually groupoids enriched in groupoids. So it's like whenever we have an inverse of two cells with respect to horizontal composition, then we can construct an inverse of the two cell with respect to vertical composition. So the home categories become home groupoids. I was wondering if that is related in a way.
It must be. I don't know how. Because
it should, right?
Please send me some references about this. I mean, I cannot be sure, but I strongly believe it's related, and I'm curious to understand how.
Okay. Yeah, I can. I mean, it's just a.
Yes, I don't work very often with enriched context. That's why I'm ignorant on this side. But I think it's related. Yes, it must be. It's the same magic. So it's
yeah, it feels like. Okay, I'll send you something.
Thank you.
All right. Are there any more questions or comments?
Feel free to ask.
No, I think the talk was so absolutely clear that nobody wonders anything. Okay, so while there are no questions, let's have a short break. We're going to start again at what in Italy is 4, so at 00, no matter your time zone. Of course, if the speaker can stay around, maybe somebody still does have any questions or...
Okay, we can do the coffee break, so, right?
Yeah, yes, have coffee, of course.
Okay.
Just don't disappear, please.